Good morning, all. Today's class is on denoising autoencoders. What we are going to see today is a specific type of autoencoder which is supposed to be more robust than the conventional type of an autoencoder. And how that is happening is just by adding an additional layer at the input, which forces the input to become more noisy. You can see here in the figure that is given, the input vector is x1, x2, x3, x4. So this is one input vector, and two of those four inputs have been made to 0. So the denoising autoencoder forces randomly some of the inputs elements. That basically, if you have say thousands of input vectors, for each input vector the algorithm will force some elements of those each input vectors to randomly become 0. So once that is done, that is the input which is actually fed into the network, and the output of the network is the reconstructed image. But when the training happens, the output of the network is compared not with the corrupted input but with the original uncorrupted input. So what happens is that the network sees only the corrupted input, but it has to learn to identify uncorrupted input. So this is how a certain degree of robustness is imparted into the system. There is also a small problem if you are working with MATLAB. The problem is that MATLAB does not allow you to add a separate input layer to its autoencoder network. So all you can do is you can specify only one particular input, and it automatically takes that as the output. So there is no possible way in which you can add another layer which kind of makes the system a little bit noisy. So what we have done in this particular example is that we have used this traditional feed forward net function to implement this network, and it will work just fine. So the second thing that we have done is we have arbitrarily made the inputs 0 by simply adding a salt and pepper noise to the network. We'll see how that is being done. Again, the same step is being followed. I'm using the same MNIST dataset just to make sure that there is consistency across classes. We are loading the MNIST dataset, which is in the form of a cell array. Training and testing data is being loaded into the system. Next step that I will do is I am just inserting a salt and pepper noise into the images. So what is happening here is that I can do that simply by using something called imNoise function. So here in these three lines, I am picking each of the training data samples, that is each of the 28 cross 28 sized images, and simply adding a salt and pepper noise with a fraction of 0.1. That is roughly about 10% of the total pixels will be modified. Out of that, some that is around half or one third of them will actually be the pixels will be replaced by uh, zeros. Similarly, one third of them will get replaced by uh, ones, and the remaining are left without any changes. Okay, so what we have done effectively is made some of the pixels zeros. This is what denoising autoencoder was supposed to do. In addition to that, what we have done is we have also converted some of the pixels into ones. So it's like adding some additional noise into the system. The network will work just fine with this. So if you look at this, next step that I have done is I have just plotted some of the images. You can see this is the result of adding a salt and pepper noise into the training dataset. So that the reason why it is salt and pepper is because you can see I have added some black dots, some white dots, and so on. And 10% is a little bit on the higher side. You usually add much lower amount of noise. Because I just wanted it to be more visible, that's why I have added d equals to 0.01, or the fraction is being taken as 0.1. So next step that I have to do is I have to define the network. My feed forward network has got 5 neurons in the hidden layer. I'm considering only one single hidden layer with 5 neurons in it. This is because, again, due to the computational limitations that I have on my personal computer, the larger number of neurons you put, the better will be your reconstruction accuracy. So I will suggest that you go for a larger number when you have a chance. And what I'm doing is, after that, what I do is I just simply train the network using the train function. A net is what I have defined already. Training data noisy is the noisy input that I'm giving. And the output, if you remember, is the training data. I'm doing image reconstruction here, which means that input should be equal to output. But if you look at this particular case, input is the noisy data, but the output should be the training data. So if it had been a conventional autoencoder, input would also have been training underscore data, output also would have been training underscore data. But because we are using a denoising autoencoder, the input is training that underscore data underscore noisy, which is the noisy input, while the output is the original training underscore data. And I'm using some, there's a built-in algorithms which you can use. You can use SCG, you can use Levenberg-Marquardt, you can use GDM, gradient descent with momentum. You can use any of those. SCG is the built-in algorithm if you do not specify anything, and it works well. So we'll use that. And what I'm using is I'm using the use parallel. Yes, this allows you to use all the parallel possible threads in your system. I have 2 threads, so I'm using both of them. And if you have got a GPU, which is an NVIDIA GPU, you can say use GPU equals to yes, it will automatically pick up the GPU and start using that. So using a GPU, if you have an NVIDIA GPU in your system, is a good idea. It will speed up your processing a lot by a large amount actually. Okay. So what we do is after that you can view the network. This will look like a single uh, hidden layer feed forward network, a typical single hidden layer feed forward network. And next, what we do is we try to find out how good the network is able to recreate the input. So training data reconstructed is net of training data. Net is the network that I have trained. Training data is being input into the net. So basically what we are doing is this is called in sample testing. We already have trained the network on the same data set. And now we are trying to find out what its performance is on the same data set. So network has already seen this data, it has learned this data, and now we are trying to find out how much error it is producing. Okay, so training data, this is actually the original training data. What the network has seen is a slightly corrupted version of this, but you get the point. It's very close to what we are actually trying to do. So the training error that you get is calculated using the MSC function. This is again a built-in function in MATLAB. Unfortunately, it also does not work with cell. So what we do is we convert that into in its underlying data type, which is a double, by using cell to mat function. So training data underscore reconstructed minus cell to mat training data. So this will convert this into the underlying data type, and MSC will be calculated using that. So you will get the training error as 0.0141. Is it good? Is it bad? We do not know. The only way of knowing exactly is by having a visualization of the data. So what we do is we just have a look at how the dataset looks like after the reconstruction. You can see this is how the reconstructed images look like. Please remember, this is what I have got by connecting a dense net. This is actually because it's a fully connected neural network that I have designed. Standard feed-forward networks are by default fully connected, if you remember. Um, and using just 5 neurons, I'm able to get a reconstruction which looks like this. I suggest that you have a higher number of neurons. If you have something like say 50 or 60, your reconstruction will be very improved when compared to what you are seeing on the screen right now. So that is done. I'm getting a reasonably okay kind of a reconstruction here. And next step that I have to do is I have to check how good it works with the testing data set. So here I'm just randomly picking about 20 images from the testing data and just displaying it. This is the testing data without any modification. All right. Please remember that when we are trying to do testing or validation, I do not have to force salt and pepper noise onto the testing data. The salt and pepper noise or the corruption of input or the making the data noisy is done only during the training phase. During the testing phase, I do not have to bother about adding an extra noise or converting some pixels randomly to zeros or to ones. I can give the data as it is because I only need to use the conversion of pixels to zeros during the training part. I want to make the network robust so that it is able to learn complicated test patterns. So in this case, I have the test patterns and I'm just inputting that directly into the network, which you can see here. Net of testing data. The testing data is getting reconstructed. I'm getting about same error that you see here. So reconstructed testing image, if you want to see, this is how the reconstructed testing image also looks like. So again, you can see it's able to reasonably properly reconstruct the image just by using 5 hidden neurons. The image is 784 cross 1. The encoded dataset is 5 cross 1. So that's the level of compression we have got, and still it's able to reasonably see things. So you can use this and play around with this, change the number of hidden neurons and see how it actually behaves. So this is how the whole process works. And why we are going for feed forward net is mainly because of the limitations that are there in MATLAB 2019b. 2020a also has not addressed this apparently. This issue has been raised with MathWorks. They are looking into this. Hopefully it will be sorted in the future releases. Okay, so that's all that is for today. If you have any questions, please put it in the comments below. Like and subscribe.